have to recognize is that if you're in an interview, right, and you get asked like a relatively easier problem, the bar for like how well you're expected to do is, also like a little bit higher. So for a pretty hard question, you might be forgiven, sort of a lot of imprecision or a lot of, like small bugs in your solution and a lot of imprecision. For like an easy problem, you just want to make sure you like sort of like, you really kind of knock it out very carefully. You don't have any bugs in your implementation, no corner cases that you missed. Another like really important skill is essentially, kind of like not overcomplicating the solution, right? So there's a certain amount, there's something to be said for kind of like elegance and minimalism of the solution. So your solution, you want to have the complexity you need in order to, you want to have the code complexity that you need in order to achieve the time complexity you're looking for, right? But you want to simplify your solution as much as possible without compromising the time complexity. So part one should be like really, really easy. So part one, you're given an array like this. Say, are the lights bright enough for everybody in this room? Everybody fine? Yeah. Okay. Yeah. So that's a little dim, but
Might be turned on.
I guess I could turn them off. Yeah, I think that's good. Okay, so so let's say you're given an array like this. You get 5, 10, 7, and 12, or whatever, 13, and let's say you're given a, let's say you're given a difference of k equals 2, right? So then you're looking for, are there any two numbers in this array that differ by at most 2, right? So are there any two numbers in the array that are like two together or closer? So the logical thing to do is to bring numbers that are close next to each other, right? So that's basically just the concept of sorting. So you should just call the sort function on this. Don't bother writing your own sort. I saw one interesting idea where somebody was like coding their own merge sort so that they could, try to detect situations where two numbers are close together kind of early before the array is fully sorted. And that's an interesting concept, and that's neat. But what I'm saying is all that's really expected that you will do for this problem is just sort the numbers in some way. So here you get your sorted array just by calling like a sort function. You don't have to code your own sort or anything. And then and then some people once again kind of overcomplicated things by saying like, okay, what I'm going to do is for every number I'm going to do like a modified binary search to find an offset of 2. So for like 10, I'll search for 8, and I'll search for 12, for example. That's like one way you could, to give one example of like what might be slightly overcomplicating it, right? If you calculate these targets and do like a modified binary search to find the spot where it would be, and then see if there's anything in that spot. But you could do it much more simply. If any two numbers are within the target distance of each other, then they will appear next to each other, or some such example will, right? What I'm saying is you can just check adjacent values. You can check 5 and 7, and 7 and 10, then 13 and 10, and if none of them are closer than k together, then nothing else will be 2. Like these two can't be closer than k together if 5 and 7 were not closer than k together, or if 7 and 10 were not closer than k together, right? So it is sufficient to just check adjacent values. If any of them are close enough, because adjacent values are the ones that are conceptually closest, right? So they're the ones that are closest to each other. For example, 5 and 10 can't be within k if 5 and 7 are not within k. So either you will find an example of two values that are closer than k together in adjacent values, or there will not be any such example, right? So it's sufficient to just check adjacent numbers. Simple for loop like, basically start at index 1 and go until index length -1, and just compare index, at any given point compare index I to index I minus 1. So, very simple for loop, like, for from I to I is less than length, and, compare I to I minus 1. And see if those differ by less than k. And because it's also sorted, you don't even have to do the absolute value, right? This number is bigger or equal, so you just do array of I minus array of I minus 1, and see if that value is less than or equal to k. So here we would detect it right away, and we would just, as soon as we see this 5 and 7, we would return false or true. Yeah, we'd return true. Yeah, whichever way the problem was phrased. Yeah, the problem was phrased that this should return true. Okay. So yeah, pretty simple. The point is, the goal is really like to not overcomplicate when you have like simple things like that. Just give kind of like the most straightforward, simple solution. Now, it is possible to solve this first problem in order n time. I'll go over a little later how to do that. If you actually solve it in order n time and your solution is more complicated, then that makes sense because you actually got something for it. You solved it at a better time complexity. But if you're going to solve it at n log n, you won't really want to keep like the code complexity, so to say, minimal, right? You want to keep your solution as simple as possible. Okay, part 2. So part 2 is basically asking, if now you only have to detect exact duplicates, but you have to make sure that duplicates occur only within the specified offset. So for example, if you have this case, right, and you have d equals 2, that is, d is like the distance limit, this would actually return false because these duplicates are within 3 indices of each other. And there are no other duplicates, right? But if on the other hand we have this input, this would return true because now these are within 2 of each other, and that's within the limit. So first question you have to ask when like breaking this down, right, is first of all, like without the d limit, how do you solve the duplicates problem? Like most of you probably already know this; it's a common problem, right? But if you didn't know this, that's the question you should ask first. Like how do you detect duplicates in general, right, without any limit? So what you can do is obviously there's like a naive, check everything order n squared solution, and that likewise works for the d case. You can give an order d times n solution where for every value you scan the last d values just in a loop, right? But that's pretty naive. Like if d can be up to n, so that would be order n squared potentially. But how do you solve the duplicates problem more efficiently, like the common one with no distance restriction? Well, the really common solution, right, is you create like a map, or like more like a set. You create a set of all the past values you've seen. Initially, the set is empty. Then, as you go through the values, for each value, you check if it's already in the set. If it's already in the set, return true. You have a duplicate. If you don't have it in the set, then add it to the set, so that in the future, if you find another one for values, you will detect it. Now here, there's just kind of this extra complication of the distance restriction, right? So basically that just means your set has to maintain a little bit of extra information about where you've seen the numbers, right? You can't just have a set of all the numbers you've seen, because the problem with that would be that when I see this 15, I need to have some information about where it was that I saw this last 15. Because depending on whether it's in range or not, it might or not be it might be triggering my condition, or it might not be triggering my condition, right? It could be past the range I'm looking for, or it could be in the range I'm looking for. So there's basically like 2 main ways to do that. So way number 1 is conceptually you could just go through the array and you could build a hash map of the indices where each value occurs. So the initial form of this idea would look like this. And since a value may occur, it has to be a list since a value may occur in multiple places. So conceptually you would build it like that. Okay, I've seen this, I've seen that. So now my lists look like that. Now I go to 7, okay, 7, and this is just like a hash map. And then I go to 15, and now, since 15 is already in here, I would append 3 to this. And since I'm appending to the end, these always stay sorted. Because I'm building this as I scan through the array, right? So the indices are going to be added in ascending order to these lists. So I don't have to do any sorting here. If you did sorting here, then you probably, that's a small overcomplication because this is guaranteed to be sorted by construction. Okay, so then I have this. Well, it turns out we can, okay, so what could I do with this? It turns out we can simplify this further, but, even if you just got this idea, right, this is already enough for the order n solution, because here all you have to do is now just, you go through all the values, right? You don't actually care what the values are, but you look at the list, and again, now you're looking for, now it's back to basically the first problem, right? Or now you want to know, are there any indices within D of each other in this list? And this is already a sorted list, so you don't even have to sort it. So now this problem can be solved in time linear with the size of this, just by scanning, adjacent elements. So this is basically the first problem now, all over again. You do have to do it for each distinct value, but consider that the time taken is linear in just the size of the specific list, and the total sizes of all the lists don't exceed n. Right? That's the analysis that shows that it's order n. There's at most order n different map keys, so that portion of the iteration is order n. And then this may take some amount of time, but it's proportional to however many elements there are, and the total number of elements across all the list is at most n, because every index gets only added in one place. Okay. Yes?
So does it have to be a list and just
the last index?
Yeah.
Yes. Yeah, and I was going to go there next. So, like I mentioned earlier, this can be simplified further. This is just kind of like one conceptual way of looking at it. But as you point out, it's, and you may have actually just come up with this idea right away without even going through this intermediate stage. But it turns out you can simplify this further. What you can say is you can say, I don't even need to store lists here. That's actually overcomplicating it a little bit. It may be conceptually, the reason I even present this at all is because conceptually, it's easy to understand, right? But from this idea, what you can do is you can recognize that there's no reason to build up these lists and then check them all at the end. Whenever I insert a new value, if I have a new value here, let's say I get a 7 here, right? When I insert 4 in here, I can just do the comparison right there, and then I don't even need my whole history. I can just keep maintaining my last element, right? Because this 4 will only be compared against this 2, and in fact, the elements that came before were never used if I'm doing the comparisons as I go. Or I only need, if I'm doing the comparisons as I go, I only need to know what my last element was. So we can simplify it to a structure like this, where as we're going through, we're just maintaining this kind of information. For every value, just maintain the last index where you saw it. So, if we've processed, let's say this array keeps going on, right? So if we've processed this far, our current, let's say d equals 1. I mean, if d equals 2, we wouldn't have processed past this point, right? Because if d equals 2, then as soon as we see this value, and we see, here our index equals 3, when at this point in the computation, we would have a record that says that 15 was last seen at index 1, and then we would see that the difference between our current index and where it was last seen is, less than or equal to d, and we would return. But let's say d equals 1. So in that case, if we've gotten this far in the computation, so the way this would get updated from the beginning is, first you process 10. Well, let's say this is the input. Let's see how it will work on, this input. So when you process 10, you store 10 was last seen at 0. When you process 15 was last seen at 1. If the record was not already in the hash map, then you just insert it, because that means your value was never seen before. Then, 7 was last seen at 2. And then 15, now I see it again, I see that I've seen it before, and I say, okay, what's the difference between 3, my current index, which is 3, and the last index where it was seen, index 1. That difference is 2. Is that greater or smaller than this? Oh, it's greater, so it doesn't count. Okay, but then I have to update this to 3. And then I go to this 7. Again, I've seen 7 before, but it's not within range. So I just update this index. And then I go to this 7. I compare, last time I saw 7 was at index 4. Now I'm seeing it at index 5. that's a difference of 1, that's within my range, and so at that point I return true. So I do have a duplicate within distance 1, it's here. And then if I reach the end of the array and I haven't, returned true, then eventually I'll return false. It's not really possible to return, before you see all the numbers, right? Because the duplicate could happen at the very end, right? Okay, so any questions about this part before I go on? So this is kind of like a very simple solution. Oh, another perfectly viable solution is what you could have done is you could have maintained a sliding window. This is actually kind of like, I would consider the two solutions about equally elegant. The one advantage of the sliding window solution is that it uses less space, potentially. So the sliding window solution is like, let's say like D equals 2 here, right? So what it is you basically just add these to a set. It's no longer a map, it's just a set. So, you add these to a set, and so far, you don't have any duplicates, so you haven't returned. And then what you would do is, before you add this 15, you would actually subtract this 10 out. So you would remove 10 from the set, because, now you're scanning this next, now you're going from this window to this window. So you want to subtract out this one element, right? And you want to add in this other element. So you would first subtract this 10, then you would try adding in the 15, and at that point you would see, I still have the 15, and therefore duplicate. Because now this only has things that are within the last D range. And at most it will be D numbers in a set at any given time. So this uses only order D space and not order N space. But D could be up to order N, so it's not really like a huge gain in this problem. But I'm just saying that if D happens to be small in your problem, you can solve it with less space. Okay, any questions before I go on to part 3? Okay. Yeah, so part 3, basically combining the two techniques, combining the two requirements. That doesn't imply that you will combine the two techniques, but it's, somewhat reasonable to think so. Now, so a sorting-based solution is a little bit tricky here. It is actually possible to get a solution just based on like simple array manipulation and sorting, but it's tricky. The kind of more obvious solution is to kind of adapt, the sliding window approach from last time. So, if we had an array like this, let's say D equals 2 and K equals 3. The idea is, let's say we have, so we want to detect if there's any values that differ by 3 that are at most, 2 indices apart. And, I don't know, here's some data. And then maybe, maybe finally over here we'll have something that matches. So let's say this is the data, right? Okay. So, easiest idea is to maintain a sliding window, or at least in my opinion, this is probably the easiest way. People can let me know if they disagree, if they think they found like an even easier way. But what I would do is I would maintain this sliding window of 2 indices, so that means the sliding window itself is of size 3. And now we have to maintain these elements 10, 5, and 15. The only tricky thing is that we need to be able to do this kind of like fuzzy match on equality of the values, right? So we're not looking for exact matches of the values. So it's a little bit harder to use a hash map, right? That was the problem. That was what we were able to do before, right? We were maintaining just hash, just like a hash table of all the values, so to back the set, right? But what do we do if we have to detect values that could be plus minus 3 of our current value? Well, the idea is you have to use some kind of ordered collection, right? In order to be able to, so what has to happen here is if I have this window initially, when I switch my sliding window, okay, I'm going to delete 10, so that means I have to have some kind of collection that supports the delete operation. There's a lot of collections that do support the delete operation, right? But there's some that don't. Like, for example, heap is out, right? Because you can't delete elements from a heap. You can delete the min element in a heap, but there's no guarantee that the element you're going to try to delete here is the min element of the heap. I mean, this is the min, right? And there's actually no generic way to delete a min from a heap. You can't actually search a heap. You can get the min value of a heap, right? But a heap is actually not searchable for a specific target value, right? unless you have like, it's possible to maintain additional data structures that provide pointers into the heap so you can maintain your search capability, but that's really overcomplicating it. So what do we need to do here? We need some data structure that supports delete. So like, hash table supports delete, tree supports delete, like binary search tree, right? Some other things could support delete. I mean, heap supports delete too, but inefficiently, right? We're looking for data structures that will support this efficiently, so that we don't do like n squared. I mean, everything supports delete inefficiently, right? Like, remove all the values, except the one you're trying to delete, and put them into a new data structure. Worst case, right? So, but that's not what we're looking for, right? We're looking for a collection that supports efficient removal, so that even if the set is large, it doesn't take a long time. Okay. Because, this is a very small example, right? Like, imagine the case where the array is size 1 million, and D is like 1 million, and K is some large value too. Okay, and then what we need to do, right, is when we extend the sliding window to this part, right, we would need to add 0. And at that point, we need to be able to check whether there is anything plus minus 3 of 0. So, anything within the whole range. So when we insert the 0, the check we need to be able to do here is we need to ask, is anything in this range part of our data set already? So before I insert this 0, I will ask, is there anything in this range in this data set? And then I will add 0. If I detect anything in this range, I'll just return true. If not, then I'll keep going and I'll, add 0 to this data set. So in other words, I need a data set where I can search for ranges of things. Now, okay, so for small k, you could envision a solution where you're still maintaining a hash table, and you just try every possible value, right? You iterate over every value in this range. For small k, that works well. However, there's no constraint in this problem to have small k. So if k is like 1 million, you would be looking over like a very large range, right? So what data structure supports efficient delete and insert, right? You need insert too. So we need a data structure that supports efficient delete and insert, and also efficient range search. So, what's a data structure that has the capability to do this? Yeah, basically a tree. So that's a simple solution. Like a balanced tree should be able to do all of these in log n, or log however many elements are in the tree. So there are at most d elements in the tree. So this solution, it'll do a constant amount of tree operations for every time you slide the window. You slide the window a total of like order n times. It's not exactly n, it's like less than n, but it's at most n. And then the tree operations themselves, so the time complexity is n multiplied by like some constant. We do like 1 deletion, 1 insertion, 1 search. So, some constant like 3 in this case. And then multiplied by log d, which is the running time of all the tree operations. This is a constant, so it can be removed from the complexity. And we have an order n log d solution. Independent of k, except for, well, obviously if k were so large that it like overflows like an integer or something, then maybe we'd need like extra storage and extra processing. But assuming like things fit into standard data types, this is independent of k, and it's n log d. We also saw another proposal for an order nk solution, right? That's just use a hash map and check everything in this range. But this is not a very good solution because k can be large, right? This scales graciously with d because d is capped to being n, right? If d is more than n, then basically, for all intents and purposes, you can assume it's n, right? If the range is so large that it covers more than the whole array, then for all intents and purposes, it's just the entire array, and this is just the standard duplicates problem. So, you can assume that n log d is capped at n log n. But nk, you can make no such assumption, right? You don't know what the values in the array are, which could be like huge numbers. All right. So finally, how do you get to the order n solution? Well, so this one is, it's really like an easy concept, but it's kind of hard to think of if you've never done it, which is why, I kind of said this is hard, don't get stuck on it. But really, like, it's not hard to understand. So the idea is you can still use hash maps. So we can still use the previous idea from part 2, where just for every value we're keeping like where class occurred. Except here's the thing: because we are dealing now with, basically because we're dealing now with the situation where we have to be careful about values that are close to equal but not exactly equal, we just have to hash on a different key. We can't hash on the value itself. So think of it this way, right? Divide the number line, like think of it like an abstract number line, right? Divide it into buckets, and let those buckets be size k. So, here's 0. So bucket number 0, well, we're gonna have like positive and negative buckets, okay? So bucket number 0 covers the range 0 to k minus 1. And then from k to 2k minus 1 is bucket number 1. So these are like bucket numbers. So, here's the number line. This is like the 0 origin point. And we'll, divide it into buckets like this. And then we're going to have a set of negative buckets too. You could keep them in the same array, but, it might be conceptually easier to think of this as like negative 0. This is the 0th index of the negative buckets. Negative 1, negative 2, and so on. You got to be a little careful with the negative numbers, because the negative numbers you'll have to adjust them by 1. Just because 0 is covered by this bucket, you'll have to be careful that, if you have a negative bucket, it actually starts at negative 1. You might run into like weird corner cases if there's overlap between your buckets. So there's the idea. So the negative 0th bucket actually covers from like negative 1 to negative k, whereas this one covers 0 to k minus 1. Okay, so what do you do with these buckets, right? Well, when a value is hashed, I'm gonna hash it based. I'm gonna record what the actual value was, but I'm gonna the hash key in the hash table is gonna be the number of the bucket. So what I'm gonna do is I'm gonna check if the number is like positive or negative, right? Based on that, I'm gonna record like, it'd probably be easier to you can do some trick to kind of encode negative and positive numbers together. Like what you can do is you can say that if you get a positive number, the hash key will be, an even number. Like if you get a positive number, you'll hash it to 2k, and if you get a negative number, you'll take the negative index and hash it to like 2k plus 1. So that there's like encoding tricks you can do, but alternatively, you can make the hash key like a boolean, boolean saying if it's negative, combined with the number. So you can have a hash key be like bool and int, with a tuple, right? Like a pair of bool and int. One is saying if it's positive or negative, the other is saying if it's, what the value is. Or actually, maybe an even simpler idea is like let's just let this bucket number be negative 1. That's actually a lot simpler. I don't know why I didn't do that. The only thing is that means that when we do arithmetic to calculate this, we'll have to remember that if our original number was negative, we have to subtract 1. So how do we calculate the bucket number? Well, it's easy. It's just truncating division, right? It's like if my number is n, the bucket number is basically if n is greater than 0 or greater or equal to 0, then the bucket number is going to be n over k. Just truncating division, and otherwise, if n is less than 0, right? So this is the case if n is less than 0, right? Then what you would need to do is, you need to adjust this by 1. So, then you would take it's n plus, so take n. N is a negative number. So I guess you add 1, and then you divide by k, and then you subtract another 1. I may have an off by 1 in here. I think this is right. Yeah. So like if you have negative 1, you would calculate 0 here, minus 1, and it would end up in the bucket minus 1. Yeah. And if you have negative k, then negative k plus 1 is actually negative k plus 1 divided by this is actually 0, and you still end up in the bucket number 1. Yeah. So it's maybe a little tricky to make sure you get the corner case exactly right. But so this is the bucketing scheme, And then what you go and you do here is for every value, you're going to key it based on its bucket. So, for example, 10, k equals 3. So we do a calculation, 10 over 3 is 3. So here's the key. So this is bucket. Bucket is the key. And the data we're going to store here is we're going to store the last index where we've seen it, and we're also going to store the value. So the like natural value itself. You'll see in a moment why it's actually necessary to store the value. So the value is 10, and the last index where I saw it is 0. So this is bucket, and this is like value, and this is index. All right. Now I'm gonna do 5. So 5 over 3 is 1. It actually is more interesting for this example if I do 6. So 6 over 3 is 2. So that means I'm gonna have this key now, and I'm gonna store this. I'm gonna store 6 and the index 1 here. So this is my map so far. Now, what's interesting about these buckets, right, is because they're of size k. What that actually means is that if you ever have something within the same bucket that also has an index in range, then just return true, right? Two things that map to the same bucket, if they're in range, return true. Because the buckets are only of size k, right? So anything within this bucket, if you ever see two values that are both in this bucket, and that are also, in range here, then return true. Now you have to be careful, right? Because the converse is not true. If I don't see another value in my bucket that's in range, that doesn't mean that I don't have a conflict, right? Because if I'm right here on the number line, I could be matching anything up to here or anything up to here, right? So, but here's the key. Here's the key. Any of that can only stretch one bucket in either direction. That's the key to the efficiency of the solution. So remember in the order nk solution with the hash map initially, we had the problem that, the range could be very large, and so we're going to have to access a lot of hash table keys. That is no longer a problem here because, basically if any value conflicts with this one, like if any value is like a near duplicate of the one that's right here, then it so happens that either we detect a duplicate by seeing that it was in the same bucket, or the duplicate would have to be in one of the two adjacent buckets. And this brings us back to why we stored the value here, because when we check adjacent buckets, we actually have to check the value. Because when we check adjacent buckets, it could be that something is in an adjacent bucket, but it's actually not a match. So, for example, when we put in this 2, well, first, when we were about to put in this key, well, first, before we put it in, we checked, is there a bucket 2? If there had been already a bucket for 2, we would have checked, does it contain an index that's still within range? If no, then we just, if it does contain an index and it's within the range, we just ignore the previous value, we just override it. If it did contain an index that was still in range, we would have just returned true. But here, we didn't have this key before, 2, so we just put it in. But then, we recognize that anything that went into bucket 2 could have elements that are, these near duplicates. We could have elements that are either in bucket 3 or in bucket 1. So we check the hash table for bucket 1. We have never seen anything in that bucket, so clearly that one is not doing anything. Then we check bucket 3. Oh, and look, we have bucket 3. So now it'll be critically important what value we had here, right? If we had had the value 9, it would be in this bucket, and it would be conflicting with the 6, right? At this point, we would want to return true. But since we had 10, we see this value of 10, and we say, oh, well, that's actually, 6 minus 10 is actually 4, or 10 minus 6 is 4. Therefore, no conflict. And so that's it. Then, you keep processing it like this. Like, for example, for 15, you will calculate a bucket number of 5. 15 divided by k, 3. So, this goes 15, 2. Then for 0, and for 5, you will check, is there anything in bucket 4? Is there anything in bucket 6? No. So nothing to do. Then 0, you'll end up putting this in the map, 0 and index 3. You'll check for bucket 1 and you'll check for bucket -1, and these don't exist, so 0 can't conflict with anything. Then when you get 10, 10 goes into bucket 3, you will see this. Aha, I already have something in bucket 3, is it valid? Well, this index is actually out of range now, because at this point, I'm at index 4, right? This range is 2, so this one is not valid, so I ignore it, and I just override it with my current index. But then I also have to check buckets 2 and 1. But they're all, bucket 1 doesn't exist and bucket 2 is out of range. So that doesn't conflict, and eventually this will return false, because there's no duplicates within range here. Yeah, so kind of tricky concept, but it's done, basically using hashing. You're just kind of doing this bucketing system to group similar values together by hash key, and avoid the situation where you don't know what key you have to look up in the hash table. But then you have to be careful that after you do the bucketing, it is actually possible for something to be in a different bucket and still conflict with your current value, right? But the beauty of it is that it would have to be in an adjacent bucket. So there's only for any given value, there's only at most 3 keys you have to check, right? You have to check your current bucket number, bucket +1, and bucket -1. Okay. Yeah, that's pretty hard. I mean, that's why I said don't spend too much time trying to get it. Okay. Any questions on this before I go on? Yep.
And the previous solution, can you elaborate how we use trees to check the range?
Which previous solution?
The second approach, before presenting this approach.
Yeah. So, well, okay. So how would you check range using a tree? Well, that's just an operation that the tree supports. Generally, a tree will have a function. Most tree libraries have a function like sometimes it's called upper bound or lower bound or lower neighbor, upper neighbor, stuff like that. So basically, given a value, you can ask the tree what are my 2 neighbor values. So you can ask, given value x, what is the value in the tree that is the highest value that is less than x? So in other words, nearest neighbor to the left on the number line, right? And then you can ask for nearest neighbor on the right of the number line. So a tree can return those and log it in log size of tree time. And if you didn't know that, you could also kind of think about how binary trees work, and you could see if you could figure out how to modify. That's a good exercise in itself. Figure out how you would modify, how you search nodes in a binary tree in order to be able to find nearest neighbors and not just exact matches. That should be if you understand how values are searched in a binary search tree, you should be able to figure out how to do this modified search where you find nearest neighbors. Right, and then when you find nearest neighbors, again, it's back to the same principle we used for the sorted one, that if anything matches the condition that it's less than k, it would have to be one of my 2 nearest neighbors, right? Yep.
So we are only maintaining one value in the bucket, right? Would that always work?
Yes.
Say for suppose I have -1 at the end, right? So I find one close value in 0th bucket, but then if I proceed and then I find, say I have k, value k. So I'm going to replace the 0th, so both k and 0 fall in the same bucket, that is the 0th bucket.
Well, 0 and k wouldn't, but let's say 0 and k -1 or something.
Yeah, 0 and k -1 would fall in the 0th bucket.
Right, but remember also that if ever 2 values fell into the same bucket and they were not conflicting, you've already returned. So if the fact that we are still processing means that those 2 values were never within range of each other. If we ever had 2 values fall into the same bucket and they were within valid index range of each other, we've already returned.
Right, but for suppose they are not within the valid index range,
right,
because b is very less.
Okay.
And b is less than k.
So this guarantees that every bucket has at most 1 value. Because if a bucket had multiple values, then we would have already returned, right? So then it is guaranteed that every bucket has at most 1 value.
No, sorry, I don't get that. If a bucket can have multiple values because the range is not met, right? D range is not met.
Right, but then we only keep the latest value.
Right, if we keep the latest value, and suppose we find a left value in the left bucket, if we find the value, now we cannot compare these 2 values, right?
Why not?
Because we already replaced the old value.
Right, but we
with the
don't
new
need to
value.
compare to the old value because the old value is out of range. So basically, if we ever are about to put a second value into a bucket, one of two things is true. Either both values in the bucket are valid, in which case return true immediately.
Right.
Or one of the values in the bucket is no longer valid and will never be valid, because if it's out of range now, then it'll be out of range forever, right? Into the future.
It will not be out of range with the left side one, right? Say for suppose I get a -4 value or in the future.
No, out of range means that it's just more than difference D with that current index.
Right, I get that. Say for suppose in this array, now we have -2 later in the array.
Yeah.
Then it would be within range for the first element that we saw in the 0th bucket, right?
No.
Both via k and via d. It can be
No.
in the range, right?
No, because again, the only time either the bucket only has one value, or the bucket no bucket can ever have more than one unexpired value, is the way to say it. I mean, if you have doubts on this, let's follow up after the session.
Yeah,
I want to continue
Yeah.
the discussion of the next problem. Okay. The second problem is the second problem, right? The road repairs. Yes. So basically, in a problem like this, where you're asked, what would the optimal way to place trucks be, right? So in this one, you're given in the first part, right? You're given a certain amount of fuel for the trucks, right? And you're asked, basically, what is the minimum amount of trucks you need? So you're looking for kind of an optimal way to place trucks on the road, right? And when you're thinking of kind of optimal ways to do things, the kind of first thing you want to do is you want to try to kind of constrain the sort of search range. You want to constrain the range of possible truck strategies you have to consider. So let's think about what kind of strategies are possible. So first of all, here's a road, right? This marker's getting kind of dim. So if here's a road, does it ever make sense to start a truck here and then go like this and then double back on itself? Does this kind of route ever make sense? You fuel up to a certain point and then eventually doubling back on yourself. Who knows? Maybe doubling back a couple times. Does that ever make sense? Well, no, right? Because there's no point in covering the same range twice. That has no additional effect, right? So basically, if we ever did a trajectory like that, it would be doing just this. Doing just this trajectory is no worse than doing this trajectory, right? So any duplicate parts like that can actually be removed and flattened, and any excess overlap can be applied at the end. So whatever truck did this, it should just go from here to here, and then go, however much this is, go that much into the future. And that's either equally good to this path, or it's even better because you might hit more things along the way. Because here you have more opportunity, to hit things. So I'm saying if you did this path, you might as well flatten it out like this, because this gives you all the same coverage plus possibly more. So it's strictly better for trucks never to double back on their paths. Or not strictly better, but it is definitely no worse, right? So we can consider that any optimal truck placement strategy will have all the trucks, going, picking a starting point, picking an ending point, and just going there. Also it never makes sense for trucks to stop before they use all their fuel because, why not? Trucks can always, a truck should just basically pick a starting point and then go forward by its total fuel amount. And then, you might ask, well, could there be one truck going this way and another truck going that way? Well, the direction of the trucks doesn't matter, right? Because this path uses the same fuel as this path. So if you wanted to, you could just see all the paths as picking a starting location and going forward, and all the trucks just move forward. They're sending trucks in different directions is not any better, right? Because any situation in which you do that, you can convert that into an equivalent situation where you don't do that. So now we've constrained our search space. We know that for every truck, we're gonna take a starting location. And at that point, we're just gonna go forward as far as we can until we run out of fuel. So then, does it ever make sense to start your truck on a piece of road that's already good? No, right? Because if over here, so if I have some road here, and let's say these are bad patches, it doesn't make any sense for me to start my truck here, because my truck will go as far as the fuel carries it from the starting point based on what it's already determined, right? So, if this is the amount of fuel, then I'll go this far. But yeah, I already know for a fact I'm not going to get anything done here, so why don't I just start the truck here? At the very least, this still has the same coverage, right? But now it'll go further because it'll have more fuel, and maybe it won't get anything more, or maybe there was another bad patch on the way and it'll get more. So again, the strategy of always starting on a bad patch is at least as good as the strategy of starting on a good patch. So you can rule out the possibility that you will have a solution where a truck starts on a good patch. Every truck should start on a bad patch. There's no point, right? You should cover strictly more by starting on a bad patch. Now, consider the patches from left to right. So some truck will have to cover this patch, right? Because every patch must be covered. That means that some truck must cover this patch. Without loss of generality, call that truck 1, right? So truck 1 will go forward until it runs out of fuel. We can go through the array. We can just calculate at what point it's going to run out of fuel. So there it is. It ran out of fuel here. Now, until we see another bad patch, we don't need another truck. But as soon as we see another truck, it's clear that there's no way truck 1 could have covered this, right? Because if we started here, we can't possibly reach here. So that means that this one must be assigned to truck 2, and truck 2 would have to start here. And then, of course, it would go forward as far as it has fuel. And, maybe that's past the end of the road. And then maybe in this example, we own 2 trucks. So that's basically the solution to part A. So basically, iterate through the patches in order. As soon as you see a bad patch, immediately start a truck. Then basically what you can do is actually, you don't even have to, you actually don't even have to look at the rest of these values. You can immediately skip ahead by F. Scan until you see a bad patch, then skip ahead by F, and add 1 to your truck's counter. And then keep scanning again until you see another bad patch, right? And if you see another bad patch, again, skip ahead by F. If you reach the end of the array, stop doing it. If you ever add or pass the end of the array, and that'll just give you the total number of trucks. So very kind of simple to understand algorithm once you know the idea. Okay, so technically the session's out of time, but I'm going to go on for 10 or 15 more minutes. If you have to leave and don't feel bad, just don't go out that door because if you read the summary it says emergency alarm. I've had people trip the alarm before by just not reading it on their way out. Yeah, just don't do that. The exit's that way down the elevator. Okay. So this first idea is simple enough. What's the running time? I mean, it's just order n, right? You might even not look at all the values, right? In theory, it could be better than order. In theory, you could do it in less than n operations, depending on the parameter of f, right? How large that parameter is. But potentially you could have to visit most of the values, right? Because f could be small, so it could be that when we find a truck, we don't skip ahead by a lot. And it could be that we spend a long time, over here. We have to go through the values one by one while we're looking for the next bad patch, right? So, it could be that we spend a lot of time there also. If the patches are very sparse, right, then after we process a patch, we could spend a very long time looking for where the next bad patch is. But in any case, we're always going forward in the array, and we're making one pass through the array. So order n. In general, it's not possible to do better because it is necessary to look, at least in the worst case, on some inputs, it's essentially necessary to look at all of the input to determine the answer. In some cases, it's not. If you have things close together, then here you don't have to look at all these, you can just kind of skip. But in the worst case, you can construct examples where you have to look at like the majority of the data. So, or it's not possible to do better than order n, and this algorithm's already order n, so we're kind of done here. All right. What next? Right. So then the second part of the problem basically asks, this is like a little bit of a harder variant. So this is like, you know how many trucks you have, but you have to know like how much fuel capacity they would have to have in order to complete the mission, right? So one thing we can recognize is, so this is essentially a binary search problem. But before we even get there, what we can recognize is that basically adding more fuel either keeps the number of trucks we need the same or decreases it, right? So what we can do is we can say, okay, if we have T trucks and we have a total of N coverage, the max amount of fuel we would possibly need is N over T, right? Because worst case scenario, right? If you have T trucks, worst case scenario is you just cover everything, right? You cover everything. You assign, you assign the first N over T units to truck 0. You assign, the second N over T unit to truck 1, right? And each truck covers, if each truck has N over T fuel, it covers this, and there's a total of T units in this array. So N over T is like the maximum amount of fuel that could possibly be required. And then the minimum amount of fuel that could be required, well, I mean, it's 0. If it's inconvenient to deal with 0, you can check that as a special case, like, is the array all true? Just a single pass before you start. So 0 could be a value, but then if you know the answer is not 0, then the minimum is 1, right? So you know that basically it must be some value between, the max value it could be is this, the min value it could be is, say, 1. I mean, assuming you've validated that it's not 0, right? So it has to be one of these values. So one of the things you could do is you could start with a minimum amount of fuel, right? And you could run your algorithm from the first part for 1 unit of fuel, and you could see how many trucks you get. And if it's too many, then you say, oh, well, with 1 unit of fuel, I needed 10 trucks, but I only have 5 trucks. Okay, so I guess I need more fuel. And you know that if you increase the number of fuel, you will need either the same amount of trucks or less, right? Because with more fuel, the trucks can do all the same things they did before, guaranteed, right? Because the first part of their journey will be the same. If suddenly every truck has an extra unit of fuel, it still cover, every truck can still cover exactly what it covered before, but now it might cover a little bit more, so you might eventually need less trucks, but you're not going to need more, right? So, simple order like n squared solution is, you do this, you try min equals 1, then, if that wasn't enough, then you try min equals 2, see how many trucks you need, and eventually you get to the first unit of fuel where you have enough trucks. And then you say that, well, that's the minimum, because I tried all the ones that came before, right? So that is like n squared. Well, it's order, that solution is order, n times n over t, where t is like how many trucks you have. So it's like, that solution is actually order like n squared over t if t is the given number of trucks. But potentially, the given number of trucks could be somewhat small, right? So, we have to assume this could be like order n squared. Improvement on this is we recognize that, why do we guess 1, then 2, then 3, then 4? Like, why don't we just start by guessing like n over 2t? So like half of the difference between the max and the min, right? So this is the concept of binary search. So what we do is we try n over 2t. We try like the midpoint, and then either at that point we have enough trucks or we don't, and then that tells us what subrange we need to search. Like if n over 2t was not enough trucks, or if when we gave all the trucks, half of this amount of fuel, we did not have, we needed too many trucks and we didn't have enough, then we need to give trucks even more fuel, so then we would constrain the search to, the midpoint, from the midpoint to the max. We would know that it's somewhere in that range. So we basically update our min to n over 2t. And if, the other thing happened, which is we did have enough trucks, and we know the value is between min and the value we tried, and we would update our max. And we would keep searching, and we keep moving the two closer together by kind of standard analysis of binary search, because you're cutting the search space in half every time. That basically means, like, our initial search range is essentially n minus t, minus 1, but whatever, that doesn't count. Our initial search range is size n over t, which means that it'll be completed in logarithmically many passes of that. So our time complexity looks like this. And then each pass has a cost, right? Each pass is not order 1, right? For each pass, we have to run the entire solution from the first part, which was order n. So then this is our time complexity. And by properties of like logarithms, well, n over t is like strictly less than log n, right? So this is definitely n log n. If the number of trucks is very large, like this could be smaller. Like if you were given like t equals n, this is actually order 1, but this is just order n. But if t is like say, to help see that like in most cases this is not better than log n, you can use this property of logarithms. Like this could be expressed like that. Or one way to think about it, let's say like t is like square root of n. So log of square root of n is still 1/2 log of n. So for many reasonable values of the parameters, like this is like no better than n log n. But we'll just write the complexity like this. Okay, then for the final order n solution, it's pretty tricky. So the final order n solution is basically kind of combining, so basically there's another idea you could have had to solve this in n log n, and when you combine that idea with this one as binary search, you can get order n. So the other idea you could have had is you could have said that actually I can solve the part A in a better time complexity than order n for some values of the fuel parameter. Not all, but some. And why is that? It's because remember how we were skipping chunks of the array, right? Well, we can optimize it even further to guarantee a better than order n time complexity for some of values of f. So remember how we had this line, right? And we had these patches, right? And we would start a truck here, and we'd go forward by f, like not even looking at this, right? And then we would go here, and now we would scan forward until we find the next bad patch. Well, this part is potentially slow. This part is fast, hopping forward by f here. It's fast. So ideally, what I'd like to do is I'd like to produce a solution that guarantees that I solve this problem in n over f time. So this should be doable, because every time I use up a truck, every time I do some work here, I actually skip ahead by f. So if my array is of size n, it should be doable to solve this in n over f time. But the trouble here is that after I skip ahead by f, I may have to do some large amount of work to get to the next patch if the patches are very sparse, right? Because I don't know where the next patch starts, right? So what I can do is once for all the instances, before I start the algorithm, I can do a pre-processing, where at every value, I store a number that tells me where the next patch is. And this is very easy. So imagine your patch array looks like this. Your patch is, well, let's say true is like a bad patch. So let's say you have false, false, true, true, false, true, false. So these are good, these are good, and these are like the bad ones. So I can do a pre-processing where, if I don't have a bad patch after me, I just say it's like -1. And otherwise, these are indices, 1, 3, 4, 6. Otherwise, I indicate the location of the next bad patch. So if I'm a bad patch myself, then the next bad patch is myself. But if I'm a good patch, then I use whatever last number I used here. So this is 5, 5. And then here it's going to be 3 because I'm a bad patch myself. Then 2. And then here it's going to be 2 again because this is a good patch. So you see kind of what this array does. For every index, Like, for example, if I just ask it here, it tells me immediately where the next bad batch is by direct hook. So this basically accelerates this to order 1. This part is gone. And so now I can solve the problem in order n over f time guaranteed. Because first I ask where is the first bad patch from 0, right? I jump here right away. I can't guarantee how large this jump is, but it only takes order 1. Then I'm guaranteed to jump forward f elements, again, order 1 time. And then I'm guaranteed again to complete this jump in order 1 time. So basically, every time I advance f elements, it's guaranteed to take only order 1. Because I, complete the array, I just do 2 array accesses to get here, or 3, or whatever. And so how does this help? So it helps accelerate our previous algorithm, which was, forget the binary search, right? Forget the binary search. You had the, one where you just try every possible value. So then how long would that take to run now? Well, we try every possible value of the field from 1 to n over t. And, this part may be a little tricky on the math, but what you get is you end up getting, you spend n over f time for every possible value of f. So what is that? It is n over 1 plus n over 2 plus n over 3. And, this is why I say, getting this part of the problem is hard, because you probably don't know how, maybe you don't even know how to do the summation, right? And this goes up to, n over whatever here, n over t, right? So how do you do the summation? Well, this is the harmonic series, so this is n times log n over t. Order, it's not exactly log, it's like order. So this is the same complexity we got before, actually. But we didn't do binary search here. This is binary search free. This was just based on the principle of optimizing it. And then finally, the ultimate improvement is you combine the two. So you do a binary search, but you are also using this technique to speed it up. This technique, where you jump around. And if you just do the analysis for that, you can, I'm not going to do it right now, but you can see that it is actually adds up to at most order n. One type of design question is just you're asked something really abstract, how would you design Amazon.com, right? And you have to come up with a whole design of all the different components. It's mostly kind of do you understand what the different components of something will be and how they'll be interconnected and stuff like that. So that's kind of more of a large kind of system overview kind of question. Then there's kind of design questions that are more invent features for this sort of thing. What features would you come up with to, delight users within this product kind of thing. So there's questions like that. This question is more along the kind of algorithms and distributed systems design question. So I consider this third question, I consider it to be a design question, but it is very algorithmically oriented. It is essentially, there's some amount of design and there's some amount of algorithms and kind of combining the two, and also some amount of distributed system stuff where you have to understand how you would translate, an algorithm that maybe in one form that's designed to run on, say, a single core, right? Like most things in an algorithms textbook are. And then you have to figure out how to translate that to say a system that has persistent storage, and maybe based on databases rather than holding hash tables in memory and stuff like that. So that usually requires a pretty good starting understanding of the concepts. So first, the way I approach such questions, and this is really important actually. A lot of people just get completely lost on these sort of broad questions, oh my god, I'm supposed to design a distributed system, right? It's this is way over my head, right? Supposed to design a distributed system to do this complicated task where, according to the problem statement, I'm processing a petabyte of data, right? It's crazy, how am I supposed to do that? Well, you have to kind of peel back and simplify. So first you have to consider, what is the most minimal thing we can make that has some, at least, of the same features that this system is supposed to have. Okay, so here's kind of a good starting point. Consider a situation where I have all the web pages on my local computer, right? So suppose I downloaded all the web pages, just in a sense, suppose my local computer has an API where I pass in a URL and it gives me the page because they're all already downloaded. Or maybe it goes and downloads it for me, but I don't really have to worry about that. So suppose I can just kind of get all the content by URL, and suppose further that I'm not required to keep anything in persistent storage. So like, this is just like, I run it and it completes, and I don't have to store any intermediate state. So basically this is just like the most minimal thing that can work, and I only have to run it on one machine. And it's not going to work at the scale that the problem asked for, right? The problem asked for, for processing like petabytes of data. That should be a very, very clear signal that ultimately you are expected to build a distributed system of some kind. But, we can't start there, because if we don't know how to solve the problem on one core, we don't know how to scale it either. There's no way that like the problem is going to get easier when you add more nodes, right? You only add complexity as you scale up, right? So we have to start at this kind of minimal base where we can hope to sort of make progress, and then we can try to peel back the assumptions we make. And when, like, if we didn't make something distributed, we can say, well, how do we make it distributed now? So we start with, suppose I have everything running on my local computer. I'm only gonna I'm not gonna worry about speed beyond just not doing egregiously inefficient things. I'm not going to worry about minimizing disk I/O or even minimizing network bandwidth. I'm just gonna I have a bunch of web pages on my computer. I just want to crawl them and visit all the web pages and download all the images, right? Okay, so how do I do that? Well, at kind of the simplest level, right? So there are web pages, and again, this is making simplifying assumptions, but this is just the starting point, right? So web pages are going to have these image tags in them, and image tags contain a URL that you can use to download an image. There's some attributes in here, like source or whatever. That's just basic HTML. You don't have to know much HTML for this, but you should know that the web, web pages are HTML. And one of the kind of assumptions that was in the description is that you don't have to worry about images embedded in Flash or hidden in complicated ways, right? We're only looking to we're not looking to download only tracking pixels, right? Well, actually, tracking pixels might be downloaded by this. We're looking to just capture the images that are explicitly embedded. That's good enough for our purposes. So the idea is that we started some main page. This is a main page, right? This was in the description of the problem. And then the main page, there's kind of two things this page might have that we care about. One is that it may have one or more images, right? And then it may also have links, right? There's basically the concept of a link in HTML, right? So there's links and there's images. Those are the two classes of things we care about. Why do we care about links? Is because links can lead us to new pages where we can discover new images, right? So the idea is we should be able to parse an HTML page. Now this is not you don't want to focus the problem on this because the problem is more asking kind of at a higher level. That's very low level. But you have to understand that at some point there's going to be a parser component. And probably you're just using an existing library for this, probably not rolling your own. But at some point you're going to have to parse the HTML page, and you're going to have to extract all the image tags and extract all the link tags. And so now essentially, basically post parser, we can think that a web URL, is a mapping of a URL to a list of links and a list of image URLs. So we can kind of think that, okay, so URL maps to a structure that contains, list of URL images and a list of URL links. And these links need to be further crawled, right? These images are basically final destinations, kind of. These links need to be further crawled. So links kind of look like this, right? The web may be interconnected in complicated ways, right? This could link to this page, and this page could link to a lot of other pages. And, certainly there can be backlinks and circular links, this page can link to this page, and this page can link to that, right? So at this point, this is essentially a graph problem. So This is assuming you don't have any of those like automatically generated links where like, you have a page that's a calendar and there's always a link like go to next week of the calendar, right? And you can keep clicking forever. So, there's also the problem of like how do you deal with these kind of like infinite links that don't add any value? And this is sort of like a harder problem that for now we're just gonna abstract away. Later we can always come back to it if we have time. We're not gonna have time in this discussion, but if you were in an interview, you could come back to that. And I would call that out. Like I would say, well, we're assuming the graph is finite because the set of pages we actually care about is finite. But we have to consider that the web does contain, pages like, say, a page that contains a calendar, and you can always click next, right? And it always takes you on to what is theoretically a different page. All right, but assuming we can get like a finite graph, which is kind of our simplest model, right? So at some point we have a graph, we just have like some graph, this is just me drawing like random nodes. This has no correlation to that. And the goal is, the thing is, we start at this node, and our goal is basically to follow the links to explore all the nodes. This list of links can essentially be seen as the adjacency list of this vertex, right? So like every vertex knows what outbound links it has. This is actually a directed graph. This should be drawn as a directed graph. And some edges may go both ways. So the web is basically a directed graph, right? And you have a start node, which is like your main page from where you start crawling. And your goal is to visit the entire graph, or at least your goal is to visit everything that's reachable from your current node. Like if there's some pages out here that are not linked to by anything, you have no way of knowing about them, so you can't do it. But your goal is to visit everything that's reachable from where you are, and so that is going to require like a standard graph traversal, right? So, simplest prototype is you have this locally. You're running this on just one machine. You implement a graph traversal where you run your standard graph traversal, but for every you're running it basically like nodes are identified by URLs in your traversal. And every time you get a URL, you have a list of other URLs you can go to, and you have this list of other URLs, and then you also have this list of images which you just download directly. Oh, okay. Now you have to put the images somewhere. Well, simplest scenario, you can assume that you just have like you can say, okay, I'd probably use an existing API to just make a call, just to get an image, right? And I would just and it would give you back the image, save it as a file. You can probably easily find an API for that. I mean, if not, this is like a component you can build, but this is like a very low-level component, so probably not spend too much time discussing that. So basically, we just do a graph traversal, and every time we reach a new node we have never reached before, every time we basically remember how something like DFS works, we remove nodes from the queue, right? Every time we remove a node from the queue for processing, what we would do is we would then download all of its images and save them. Now, it could be that, one interesting question to ask your interviewers, could it be that different pages have the same images? Could it be that even though a page is different, it has the same images? And the answer is yes, probably. So then you might do an additional layer of deduplication where maybe first you crawl this graph, and instead of downloading the images, maybe you don't download any images. You just whenever you remove a node from the queue, you add all of your image URLs to a hash set to deduplicate it. Or you can insert into a DB, right? If you're kind of thinking ahead to the solution where we're going to have to persist the data. And then eventually we have a separate process that goes, once we have the set of unique image URLs we want to download, we go and download it. Alternatively, what we can do is when we first process a page, we can have a hash map of all the image URLs we already downloaded, or a database of them, and we can just check each one against that. And if we have not downloaded it yet, go and download it, save it on the hard drive, and then insert a record into the database saying we are downloading it. Now, of course, this doesn't address failure. If you cut out halfway through the process, you're not going to get the correct result, right? You don't have a distributed system. This is very small scale. All right. So then we have to start thinking like, okay, how do we scale this up, right? So there's basically two aspects here, right? So one is just kind of like data downloading, right? This is just like when you are actually downloading images, you could first parallelize that part because you could recognize that that part is probably the slow part, right? Like downloading all the images is probably a slow part. Crawling is probably a bit faster. So what you can say, crawling, parsing, processing things locally, probably all a bit faster. So maybe one thing you could say is first we're just going to keep all the work on, like one node, but we're eventually going to outsource like parts of it. We're going to make parts of the system work in parallel. And then eventually we'll keep an eye out for, making the whole thing be distributed. But actually, probably the first thing we want to parallelize is the data storage, right? So when we download images, eventually we're going to have a whole lot of them, right? So, okay, so first of all, let's get a distributed data store. So, maybe we just use some kind of databases, just like a key value store. So the key is going to be the image URL, and the document associated with the key is just the image itself. And so, and then we just kind of like NoSQL all the way. Just key value stores all the way. And there's already like existing technologies we can use for that can be like scaled to like an arbitrary number of DBs, right? And can keep the data distributed. So at least now we have a place to put our images as we download them. The next thing we probably want to do is, not look to make the work distributed yet, but look to make it so that like we can, resume the work if we stop halfway through. Because one of the worst things about having it run in a single core is that, for some reason, power goes out, you have to start all over again, right? And, or just your machine may run out of RAM, keeping like all the URLs, right? And you can do kind of order of magnitude estimations to see if that will actually happen or not, but, okay. So then, so then you have this. What time is it? Yeah, just like, I'm just going to talk about this for like 3 more minutes. So you have this. So first thing is probably let's persist everything into a database. So at this point you've discussed, how you would take all of those like components of of the breadth first search, the breadth first search graph to be implemented, and how you would make it, have a persistent state in the database. So this isn't like super hard. Basically, what are like the key parts, key like state of a BFS? If you decided to do BFS, well, remember that there's a visited map, right, that keeps track of all the locations you've already visited, so you don't ever process the same node twice, right? And then there's the, so there's the visited map, and then there's the queue, right, the queue of pending items you have to process. So a queue could just be like, at the simplest level, it could just be like, a single database where, you insert basically like an incremental ID into the database, right? And your database has like an index, so it keeps it sorted by ID. And basically, whenever you need to add another item to the queue, you kind of add it to the end of the queue by giving it a larger ID. And then at any given time, when you need another work item, you pick up the item with the min ID. And so that's how we would like maintain like a simple queue within a database. Not the most efficient solution, but at least it keeps it persistent. Then the next thing would be what happens if how do we keep the visited set persistent? Well, that one's actually really easy because you just have a table keyed on the URL, and you look, or maybe on some hash in the URL, because the URL itself is like kind of a long string. So maybe it's you calculate some like 160-bit hash or whatever of the URL, and you key on that, and you have a table that contains this set of what URLs you have. Or even just the hashes. I mean, if you assume that there'll never be a hash collision because you're using like a really good like hash function, like using like a good like maybe not cryptographic, but whatever you're using like 160-bit hash function, getting like a really, or maybe more bits than that, getting like a really detailed hash. So then you know, your interviewer might ask you, well, okay, how do you make sure that, like, if the power goes out while you're in the middle of processing an item, so, like, you removed an item from the queue, right, because you were processing it, and then power goes out. How do you make sure that you know to still process that item when power comes back on? Because you already got rid of it, you took the work, but then you never actually wrote back the results, right, because you have this, like, point of failure in the middle. And at first you might say, well, okay, we can assume that if that happens, we'll lose a little bit of what we should have done. And that's bad, but, you know, it's not a big deal. We'll get close enough to the correct answer. But then, you know, how would you, like, are there strategies you can use to mitigate that? So what you could do is, for example, you could have, like, an in-progress table in your database, right, where, like, you know, maybe in an atomic transaction, right, you do something like remove from the queue and put it in the in-progress table. And then, you know, if you are resuming a run, you would check, is there anything that's got, like, stale from the last run in the in-progress table? And then you would put it back in the queue if there are things that, you know, were in flight last time the operation was aborted. So, you know, there's things like that you could talk about. Well, and then you start scaling up parts of the system, like, you know, probably first thing to scale is, you know, you create a system for downloading the images, which is like a system to which, you know, can have many nodes and has a load balancer, and you just send it requests like download this image to be working in parallel to download images, and you can have a load balancer, and so you can make like an image download service, and then your crawl only has to worry about crawling the pages. It doesn't have to wait for the images to download. Whenever it finds images, it just dispatches them via an API call to your, you know, now parallelized image downloading system, because that's the part that's actually slow. But then, of course, at large enough scale, even the crawling on a single machine slows, and you have to talk about, well, how would you actually run a BFS on multiple machines in parallel? Well, that's actually tricky because remember how BFS needs to maintain certain state, right? Like a visited set and a visited queue, right? But the problem is the visited set has to have all the pages, right? So how do you do that if you don't want to cross machine boundaries, right? So you have to come up with a solution where you do something like, basically, think of it this way, if you have like n machines, what you will do is for every URL, you will calculate a hash, and you will take that modulo n. And that will be the number of the machine. So you'll basically kind of like do like a hash calculation to, oh yeah, we're about to get out of here. Yeah, so you'll do a hash calculation to figure out which machine it would be, and then basically every machine will be responsible for maintaining the visited set of just the things that hash to it, and then crawling just the pages that hash to it. And then you could, you know, make the computation, you know, make even the crawling distributed. So, yep, we're out of time, but this is like, I mean, we're out of time half an hour ago, sorry for that. But I think the presentation was helpful to people, so better to keep going. Okay, so that is it for today.